As I said, my name's Hunter Payne. I'm a staff engineer at Credit Karma. My previous life, my previous job was to design high-performance middleware that did millions of events per second per core. I spent about a third of my career doing high-performance software. And this is sort of my ideas that I've sort of distilled over 20 years of writing software. So what are we going to talk about? Well, first we're going to talk about why do we do latency? Why don't we just, write something, that works and then call it a day, go home? I certainly prefer that. Then we're going to talk about a great slide given at a Google talk about 7 years ago called Numbers Every Programmer Should Know. We're going to talk about how to analyze those numbers, how to utilize those numbers, how to figure out how to apply those numbers to optimizing our software. Welcome. Thank you. And then we're going to look at how to benchmark our own applications, our own hardware, to know how to improve the performance of our own applications. So why does latency matter? Well, why do we do all the extra work? For example, Google, the very front of their microservice architecture is actually custom hardware they have made themselves. They actually remade the hardware of the computer to better suit what they were trying to do because they thought latency was that important. People write programming languages designed around latency. They reorganized their entire company's engineering departments around trying to squeeze latency. And why do we do this? Well, ostensibly, we do it because it saves hardware, which is nice. It makes our friends in systems operations lives a little bit easier, which is a good thing. And in a perfect world, that would be enough. But the truth is, neither of those are the real reasons. The real reason is because users hate to wait. And if you make them wait, they will go somewhere else, and they will take their money with you. So it's important to note that there's both human scale latency and machine level latency. Human scale latency is the amount of time humans can perceive. This is where we're going to optimize our applications to. Machine scale latency, we're not really going to talk about today. That would be in high frequency trading or things where you are racing against another application somehow. So what is fast? How do users perceive fast? Well, that's about 100 milliseconds. That's fast. If you can get your latency into the hundreds of milliseconds, your users will perceive your application as being instantaneous, something where they can try something and experiment with your website and interact with your website, and it won't really cost them too much. And they'll like it the best. They will rate your application in the most favorable ways, and they will have the best response to your application. At about a second or seconds of latency, the application will feel to stutter a little bit. It will feel not exactly fluid. Users will start to get a little frustrated. They'll know that, okay, if I click on this button, I got to wait for a second, or if I click on this button for wait a second, so I'm going to think about which button I should click on, and I'm going to put more thought into it. And that's going to sort of cut down on the interactivity. And if your latency goes into the tens of seconds, you've lost them. They're going somewhere else, and they're going to take their money with them, and their attention, and their eyeballs, and whatever else pays our salaries. So Amazon found that for every 100 milliseconds of latency, it costs them 1% in sales. For Amazon, that's $600 to $800 million a year. Okay, so that's why they get to put teams and whole programming languages to work to try to squeeze this stuff. But even for smaller organizations, that can really help. Google hadn't ran an experiment where normally Google returns 10 links per page, 10 search hits per page. Well, they asked users, well, how many search hits do you want us to return in the first page? And more is better, right? So if 10 is good, 20 is better, 30 is even better than that. So they're like, fine, all right, we'll put 30 on there. Well, it turns out what happened when they put 30 links on their front page is the latency of their search response page went from 300 milliseconds to 800 milliseconds. And that alone was enough to cost them 20% of their revenue. Even if your latency is very bad, just making it less bad will have a lot of impact. And Mozilla or AOL found that the users that got lucky, that had the fastest latency that your site responded, those are the ones that are going to go deepest into your site. So it really shows that if you can spend the extra time to optimize your software, optimize your infrastructure, reduce your latency, it has a massive impact on how the users respond and how deep that they penetrate into your site. So this talk was originally inspired by a talk given by Jeffrey Dean of Google entitled Building Software Systems at Google and Lessons Learned. And about 2/3 of the way through that talk, the talk was sort of a natural history of the evolution of Google's infrastructure. And it was pretty interesting, but about 2/3 of the way through the talk was the most interesting thing for me, which was a slide entitled Numbers Every Programmer Should Know. And it put into one slide something that I had struggled to explain to other developers for probably 10 or 15 years at that point. I could never figure out how to explain how to optimize things, and this sort of put it into focus. And I think that the reason why they originally made it is to settle arguments between Google engineers, because arguments between engineers can last till the heat death of the universe. So the idea was to come up with a chart where you look up on this row, you look up at that row, who has the right-ish answer, and which technique you should try to implement and measure. So let's go ahead and look at the numbers. So in the center column, you see the results in 2005 from the benchmarks, and in the right column, that's 2017. And see at the top, you can see various operations that you'll often do when you're writing a piece of software. And they're just common operations that you can benchmark, and then you can identify in your own software, and you can sort of find, this is roughly how long this could take. And my hypothesis about the original argument this was made to settle was whether compression was going to speed up the latency of a microservice. So you can see there's two rows right here. Compress 1 kilobyte with Zippy, and send 2 kilobytes over the network in the data center. And the interesting thing about this for me is that the correct answer, the most optimum solution in 2005, is different from what it would have been today. So the developer who was right, and in this particular case, compression with Zippy was much faster than sending the data over the network. So the extra bandwidth you saved by compression, turns out that actually reduced the latency because it reduced the amount of bits that the network stack had to read. And so it turns out that the correct answer in 2005 was to compress things. But today, the correct answer would have been not to compress things. It turns out that the CPU time that you would waste would not be worth the extra latency you would get. So that's kind of interesting to me. That shows that you really want to run these benchmarks every so often. Hardware changes, and just because the answer was correct last year doesn't mean it will be correct next year. So what do the numbers tell us? They tell us that CPU and RAM is obviously very fast. Acquiring and releasing locks is very, very fast. Networking inside the data center is fast, and it's getting faster. You notice that actually had the biggest jump in improvement in that 12-year period, improved 64 times. So networks can transmit 64 times as much data per unit time as they could when those benchmarks were originally taken 12 years ago. They tell us that copying data is slow, but it's getting faster, but it's still very slow in comparison with locking. It tells us that disks are slow, SSD is less slow, but we already knew that. And it tells us that networking outside the data center is slow and it's not changing. I'll let you guys guess who's responsible for that. So let's go and revisit that slide again. But this time we're going to only look at now, because we're not in 2005. I don't have a time machine. You don't probably have a time machine either. So we're going to look at the operations, and we're going to look at the order of magnitude into which the duration of the application falls, or duration of the operation falls. So you can see that you have the very slow round trip to the Netherlands. That's in order 8. You can see you have disk operations. Those are both in the order 6. That's not really surprising. And as you get to the faster and faster operations, you get to obviously a lower and lower number. Generally, you want to analyze any operation in a particular order of magnitude is roughly equivalent for your analysis. Trying to hone in on exact numbers in optimizing software is probably not going to get you much. What you're really optimizing is the most expensive operations. And the most expensive operations are the ones that appear in the highest order of magnitude. So even if the operations don't take the exact same amount of time, if they're in the same order of magnitude, you can sort of analyze them similarly. Anyway, so some of you out there are probably paying very close attention, and you saw a couple numbers up there that did not make any sense. They certainly are surprising to most people when they first see them. In this particular case, the 500,000 nanosecond round trip and the 125 nanosecond speed for writes. So how can a write be 1/4000th as fast as a ping? That doesn't seem possible. And it clearly isn't. What's happening is that that write is an amortized amount of time. It's not actually how much time it takes. It's actually the amount of time that it's responsible for taking up in the amount of time, the amount of data that you can send during one round trip. So for instance, in this particular example, our requests are 2K, and we can send 4,000 of those requests every time that we do a ping. In the amount of time it takes for a ping to complete, for that network packet to travel to the other side and back again, you can send 4,000 of these 2K requests. So it's important to understand the difference between latency and throughput and the fact that they're not exactly the same thing, but they're also not exactly inversely proportional or inverses of each other. So let's talk about that a little bit more. Latency is obviously the amount of time it takes for a particular operation to complete from start to finish, one operation. Throughput is the number of events per second you can process. You can think of latency as being how long a road is or how fast a car is traveling on the road. And throughput you can think of as the number of lanes in the highway, how wide the road is. Is it a superhighway or is it a dirt path through somebody's field? So generally when we build software infrastructures, there's a couple different design patterns that we use. It turns out knowing what you're doing, knowing are you optimizing for latency or throughput is important because that sort of tells you which kind of design patterns to use. A lot of people use microservices and they understand the benefits that come along with that in terms of organization. But from a technology point of view, from a computing point of view, microservices are used when you want to squeeze latency. When you're not squeezing latency, you use different design patterns that I've sort of called data pipeline, for lack of a better name. And those are applications that are going to be optimized for throughput. And you're going to design those applications differently, and you're going to use slightly different design techniques when you're doing a microservice versus a data pipeline. So it's important to know when you're starting out and writing a service, which of these two goals you're trying to go for. So microservices, as we said, are good for organizing teams. You will also tend to, when you're writing a microservice, you'll tend to pre-cache or pre-allocate buffers and what have you in terms of individual requests. So you might, if you allocate buffers, you're going to allocate them as to the size of the maximum request that that service can handle. It also is nice in that it keeps developers from doing things they probably shouldn't, like calling library methods that another team wrote that may be scheduled for deprecation or something else along those lines. They do have more overhead due to you having more teams, but that's for somebody else to talk about. Why data pipelines? You do a data pipeline when you're trying to get as much data through your system as possible. Generally with data pipelines, you're going to use back pressuring techniques. You'll pre-allocate buffers and other sorts of system resources in terms of numbers that are good for the hardware. For example, you will often allocate buffers in blocks of 4 kilobytes each. Why 4 kilobytes? Well, that's the size of a page in virtual memory or a page on disk. So it turns out that actually malloking 4 kilobytes, 4,096 bytes, is faster than malloking 1 byte. The reason for this is that if I'm only malloking 1 byte, I have to first find a page that is either free or partially free, and then I have to see if there's a 1 byte run on that page, and then I have to actually update that page with the information that says this byte is now allocated. If I'm allocating 4 bytes, if I'm malloking 4 kilobytes, all I have to do is find a new page. It's much faster. And so often in data pipelines, you're taking advantages of these sorts of tricks in the hardware, and that allows you to squeeze your throughput. You should never do that when you're doing a microservice. Microservices should be sized for 1 request. So now that we've talked about overall design goals that we should be looking at, now we'll talk about how you hone in on specific parts of your application to know what to optimize. So the first thing to realize is something that I'm sure you all already know, which is that not all lines of code are run the same number of times. You got some code that runs at startup, you got some code that runs at teardown, hopefully, and then you have code that handles individual requests. Code that's going to be, and also on top of that, you might have code inside the code that handles individual requests that runs multiple times per request. The most frequent run of code would be known as the inner loop. Generally, you're trying to optimize the inner loop. You're trying to pull as much operations out of the inner loop. You're trying to pull any expensive operations out of an inner loop as you can. And if you look closely at a database, the actual architecture of the software of the database, you'll realize that about 90% of it doesn't touch rows ever. It never touches the data that actually gets returned to you when you run a query. 90% of the code is actually things that are doing strange or doing novel techniques to pull work out of that inner loop. There are whole components in databases that their only job is to figure out how to do one less operation per row inside that inner loop. And that's sort of the ultimate lesson and the ultimate evolution of a highly optimized architecture in the software industry right now. So I'm sure everyone is familiar with big O notation and complexity analysis. If not, then go to an interview and you will become familiar with them. Generally, you can do the same sort of analysis here. In this case, you're looking for operations that are in the highest order of magnitude, and you sort of want to treat them as what you're analyzing. You only want to look at the frequency of the most expensive operations. You don't care about less expensive operations, just like big O notation. And you want to then find the most expensive application or operation that's run the most number of times, and you want to figure out how to reduce or eliminate those calls. This is the single best way to optimize your application. So how do you do that? What things can you do to sort of save or reduce these expensive calls that your application might need to make to carry out its use case? Well, the first one is that you can just call the operation once. You can take whatever it returned to you, and you can reuse that thing. So an example of that would be like pre-allocation or caching. In pre-allocation, when you pre-allocate the buffer, malloc is the expensive operation. And you're using the result of it, the buffer that it gave you, and you're going to use it over and over and over again. You can also make the operations less expensive. So for instance, if you're doing parsing, you might want to use a SAX or callback style parser instead of a DOM parser. The reason for that is, like I said, malloc's very expensive. DOMs are going to require allocating an awful lot of memory to hold the entire document in memory. And whereas a SAX style parser only needs to hold enough memory to hold all the data from the root to the leaf. And if you have to actually allocate less memory and you're reusing that memory, it's in the caches, it stays in the caches. And it's going to speed up your operations. Compression is another way to do it, but often data centers networking is so fast nowadays that it doesn't help so much. But that's a nice technique. You can call the expensive operation less times with more data. So for instance, batching a bunch of database writes. Or, and this is my favorite one, you can be tricky, in which case you don't do the expensive operation until after you've returned the result to the user. So for instance, metrics collection or user behavioral collection, this would be a good example of that. So we have a couple applications at Credit Karma that after they return the response, then they do something else, and that the user doesn't see that extra wait time. And honestly, if you can do the last one, that's the best one. Well, the first one's the best one. The last one's the second best one. So let's try to put some of this stuff into practice. So let's imagine we have an example application. This example application reads some JSON data over the network. Maybe it's HTTP. It'll parse it, it'll transform it, and it'll write it to the database, or write a row to the database. Should we focus on optimizing the networking, or the parsing, or the transformation? How should we optimize this app? Say we've written it, it's in production, it's running, but we want it to run more efficiently. We want it to run with lower latency. So here's a couple benchmarks of those common operations from the previous slide. You can see we have the 4 different more expensive operations. And that's roughly how much time they take in terms of benchmarking. So what do we want to do? How do we want to optimize this application? Does anyone have an idea? Say again? Yes, that's actually correct. Thank you. Networking latency is 1 round trip plus 1 write. The latency of parsing 2K JSON objects is roughly 10,000 nanoseconds, 10 microseconds. Same thing for the transformation. And the duration of writing the row, like we said before, is very slow. It's 5 milliseconds. So if you can get away with it, the correct answer in that case would be to batch up your rows, and maybe you only do 1 write every 128 requests, one commit every 128 requests. In that case, that would actually improve your latency 90%. You would be able to respond in 1/10 the time because it was far and away the most expensive operation. And 1% of the people, or maybe if we could do batch up 500 requests, then that would be 2/10 of the population. Well, they get unlucky. Their latency is going to be much higher, 5 milliseconds higher in this particular case, or 5.5. But the other 99.8% of the people get a much faster experience, and that might be a really good trade-off depending on what you're doing. So it's important to understand your use case. It's important to understand what trade-offs you're willing to make in terms of concurrency or consistency, or even accuracy. And sometimes sacrificing a few of those things will open up optimizations that allow you to really reduce your latency or really drive throughput depending on what you're going for. So instead of focusing on the JSON parsing or transforming, that's clearly the wrong thing to do. You optimize the network performance. Thank you for that. And this can be done by batching the DB writes. Compression also might be something that works in this particular case. Compression works when often if you have specialized hardware that's doing the compression, that will speed things up to the point where you can take advantage of it. But often modern in-data center networks are so fast that compression is not really as beneficial as it used to be. So I guessed here, this is what I think that application would look like in terms of a load profile. And it would probably look something similar to this. We have similar applications at Credit Karma that look roughly like this. And so generally, when you're running your application, if it's running at full bore, if you're load testing it and you have it running right at peak, the maximum number of requests it can handle, you'll get one of these three measurements will always be nearly pegged off. It will be 90% or higher. That's your bottleneck. That's the easiest way to figure out what to optimize when you have an application you're trying to optimize it. Which of these 3 things are you using almost all of? If you're not using almost all of these 3 things, there's a couple possibilities. A, you may not be throwing enough traffic at your particular application. Maybe it just has that much extra spare horsepower to go. Or maybe there's something horribly wrong with your code. But generally, you will get a picture like this where one of them is pegged off nearly scale high. And what you want to do is you want to try to optimize the operations that most heavily use that resource. So some people might look at this graph, this particular diagram, and say, OK, you should do asynchronous, right? We should be doing asynchronous networking. That's what's going to improve this here. Turns out that's not actually correct. So we benchmarked blocking versus non-blocking, and it bears out some interesting results. So the first thing to note here is that blocking I/O is often faster, especially for writes. That's very strange. Most people do not realize that. Also, the reads are almost identical speed. They're almost identically the same amount of time. The one trick here, though, is that when you run these benchmarks, we noticed that for the blocking, we expected this, but we noticed for the blocking I/O, the CPU would be much higher when we were running the blocking benchmarks versus the non-blocking benchmarks. And the reason for that is that asynchronous I/O, whether it's networking or disk, what it really saves you is CPU. It doesn't save you disk or networking. And that's an important thing to realize when you're trying to optimize these applications, because a lot of people are confused about that. You should only use non-blocking when the CPU is either overloaded or you want to reduce it. You have an active reason to want to reduce your CPU load. That's when you use asynchronous. And how much global shared state you have is sort of the ceiling on how much use you can get out of that extra CPU time. So you can often, the benefits of non-blocking is shared overhead. So it's important to understand what's happening when you're using a blocking API, all right? So when you're using, at the lowest level, all I/O is asynchronous. When your disk receives a new buffer, or when you're reading from a disk and a buffer has been filled by the disk hardware, that sends an interrupt to the CPU. When the network writes a packet out and knows that the write has completed successfully, that sends an interrupt to the CPU. At the lowest level, all I/O is fundamentally asynchronous. What's happening is that the folks that wrote the OS or the blocking APIs you're using in your language have written the code that glues together those events into a synchronous stream that lets your API work in a blocking way. But if, say, I have 4 or 10 or 100 of these blocking writers or readers, what that's doing is introducing a tremendous amount of overhead. When you're doing asynchronous programming, what you're doing is allowing one shared piece of software, piece of memory, to handle all of the overheads of all of those different write operations that you're doing. All right, and that's why it saves CPU, and that's why it doesn't really have an impact on networking or disk utilization. And the surprising thing for most people is that usually you can max out the hardware by doing blocking operations. That surprises a lot of people. Generally, you'll also max out your CPU at the same time, or at least come close to it. But then that's why we have non-blocking, so that you can save that CPU resource. So say somebody went and changed our application to non-blocking. This is what we would expect. The CPU has now gone from 25 to 3, but our application has the exact same performance profile that it did before. In other words, it has the same latency and it's handling the same number of requests per second. So it's important to understand when you use asynchronous I/O what you're getting out of it. What you're getting is more CPU, not more disk or more network. So the message is benchmark it. Hardware changes over time. The numbers that I'm reporting are probably not the numbers that you'll get, because the hardware I have at Credit Karma is probably not the same as the hardware you have wherever you are working. And certainly in the numbers that every programmer should know, I wish Credit Karma's ping times were that low. We have a really good network, but that 500,000 nanosecond number, that's an incredible network. The Google folks really know what they're doing. And so you have to benchmark it for yourself, because often you'll be surprised by these things. And these things change over time. So for instance, you'll see in a second when we talk about is instance of, I've programmed Java for 20 years, so is instance of is evil, as far as most Java programmers know. But it turns out at one point they actually optimized that. We'll talk about that in a second. But things change. Your programming language optimizes certain containers, certain runtimes. Those things improve over time. The OS improves over time. The hardware improves over time. These things change, so you have to benchmark it for yourself when you're optimizing these things. So we did some benchmarks. We used JMH, which is the Java Micro Benchmark Harness, which you can use from Scala. And I did the benchmarks on this trusty little laptop here and an M3 Medium in AWS. And I report what's being reported are the averages of those two numbers. And you can go and download the benchmarks for yourself and run them yourself and see what they tell you about your own hardware. So we saw the numbers that every programmer should know. We thought, all right, what are some other benchmarks that we might want to do? What are some other performance numbers that we're curious about, especially for the Scala language? What is it good at? What is it bad at? So we benchmarked system calls like random and current time. We benchmarked some I/O operations, as you already saw. We also benchmarked some less common I/O operations like deleting a file or updating its metadata. We tried to benchmark mysterious things like context switches, but failed. But we did find a good number for them. We benchmarked searching large data structures, and we benchmarked switch statements with classes versus integers. And we were surprised by some of the numbers and not surprised by some of the numbers. So we weren't really surprised. System calls are really fast. The Linux kernel team is really, really good. They write very efficient code. The next one, the match against 6 classes and the match against 6 integers, that one we were very surprised by. Like I said, I programmed Java for a long time. Is instance of is slow, it's evil, never call it. You're doing something wrong if you call it. However, when you do a match statement in Scala and you match against the class, well, that actually in turn will call isInstanceOf. And it will do it with an if-else structure until you get to 6 items. When you get to 6 items, it'll actually use a jump statement. Turns out that runs at the same speed as the if-else for the most part. This was very surprising to me. I had seen some Scala code in a JSON library that will remain nameless, where they had done some very clever Scala tricks so that when you matched against the results of the DOM they had parsed, you actually matched against integers instead of classes to try to avoid this. Turns out that we don't have to worry about this. This is something that we can just blithely ignore. It's great. JVM team did a really good job. isInstanceOf now runs almost as fast as integer comparison. So any Scala library where you've done some tricks to match against objects or integers instead of matching against the classes, you don't have to do that anymore. You can just match against the class. Be very naive about it. It produces cleaner code. It'll run just as fast. And this is something I would not have thought at all. And I was very surprised by this. So this is why we benchmark, because we learned things that we thought had been dogma for years. In the case of isInstanceOf, that had been dogma for 15 years for me. Anyway, so context switching, we found a good number from that from the Intel website. The other surprising thing for us is that list is glacially slow. There's only one use case where you should ever use list, and we'll talk about that in a second. But don't use list, don't use seek. They're very, very slow. You can use them if the data structure is small. Who cares? It doesn't matter. It's not going to impact performance. But if you're holding more than literally 50 items, don't do it. That's literally the cutoff where list starts really trailing off from the performance of array and map. So we're going to dive a little more deeply into 3 of these benchmarks. The first one we're going to dive more deeply into is the recursion and loops benchmark. We were trying to compare different techniques for accomplishing looping that you have available to you in Scala. Since Scala is a functional language, you have a lot of them. We use factorial as sort of our benchmark to test this stuff. We benchmarked loop for comprehensions, recursion, tail recursion, and fold left. And we expected these results to be roughly equivalent. We expected that pretty much all these techniques would run in roughly the same amount of time. We discovered a few interesting things. So the first is, this is the code that we used to benchmark this stuff, or we thought we were going to use to benchmark this stuff. At the top, you can see that @param. That's a JMH annotation that basically tells JMH to run this benchmark multiple times with different values for start. Start is simply the size of the problem we're working on in this case. @benchmark indicates that this is a benchmark that we're going to run. I tried to make the code dry, so I created a sort of more generic implementation that they would all call and use the clever implicit integral and did a clever little fold left at the bottom there that we're actually measuring. And I was very proud of myself, and I thought this is very functional code, and all the folks at the Scala Days will really be impressed by it. And unfortunately, it's wrong. I'm sorry. It turns out that the Scala compiler has some performance bottlenecks in it. It turns out that maybe someday this will be fixed. I really hope that they fix this stuff. But right now, when integral is actually a subclass of numeric, so this applies to numeric and integral. When you import them in this style and you use things like 0 and 1 and plus, the Scala compiler has not figured out how to get rid of all the auto-boxing that comes along with that. And so it turns out that the right way to do it is this, which is even shorter. It's much less dry. I basically just had to write it 4 different ways. And you can see it's basically doing the same thing. And this is what we use to benchmark things. And so this is what we found. We found that for and while are basically the same speed. So for you out there that value functional or a pure functional, and I'm sure in this room that's 80, 90% of you, go ahead and use your for comprehension. That's what you want to use. That's going to be the fastest. So this only applies to performance critical sections of your application. The rest of it, do whatever you want. And so for and while are roughly the same speed. When you get to lots and lots of iterations, while will slowly pull away from for. So if you're iterating millions of times, then maybe you want to use a while. But generally, those are the 2 fastest things. we were surprised that tail recursion was so slow. We thought tail recursion was going to run at the same speed as the for comprehension. Turns out that that's not really the case. It is significantly slower. And for some very strange reason, fold left was the slowest of all. Maybe someone can find a bug in my benchmarking code. I'm not certain why that would be the case. It compiles down ultimately at the bottom of its call stack to a while loop, so it should be the same speed as a while loop. The second benchmark that we're going to go a little deeper into is the collections benchmark. In this case, what we were trying to do is measure the speed of finding an item in a large collection. So we measured two different ways of searching the collections. We used the while loop, and we used a find with a zip with index. For the map, we used a get. Map is sort of cheating. We wanted to see map against the other data structures, though. We used different types, and we used the immutable variants of all of these basic Scala collections. And this is the benchmarking code that we use. This is a chunk of it. This particular chunk does the find with the zip with index. It's doing it for seeks, I believe. Yes. And you can download all this code on GitHub and find all the things that I did wrong. That was a joke. Anyway, so after we measured it, we found this. We found that list was very, very slow. Array was far less slow, and map, not surprisingly, was the winner. But what was interesting to us is that the difference started really early on. Even at 60 items, 64 items, the difference was an order of magnitude already. The break-even number that I've been using for when you want to switch, when you want to basically ban the use of list was about 50. So anytime you get past about 50, don't use list, don't use seek. At least if it's in performance critical code. If it's not in performance critical code, then doesn't matter. And the third and final benchmark that we're going to dive a little bit more deeply into is mutability. In this particular case, the task was to insert, delete, or read from a data structure. We wanted to compare the immutable variants to their mutable variants. We saw that array and map were the best from the previous benchmark, so we're doing the mutable and immutable variants of array. Mutable buffer, which is the growable or shrinkables array thing in Scala, and immutable index suite. And we included Java concurrent hash map for fun, and also to sort of see how locking compares to copying. And so this is a piece of the benchmarking code we used. The weird thing that you might see up here is that BH : black hole part. What that is that's a JMH data structure that basically tells the compiler not to throw away the result of this operation. So it turns out that if you were to run this without that, the hotspot in its grand wisdom will actually remove your entire read operation. It'll run very fast. You get very exciting numbers, but very wrong. Anyway, so these are the results that we got. So the first thing that was surprising is that immutable map is very slow. And we're not that surprised that it's very slow at inserting or removing. I mean, that's sort of the cost that you would pay for using an immutable data structure. But its reads were very slow too, which was very surprising to us. Compaction is a big problem for arrays. So the only time that you should ever use a big list or a list with a lot of items in it is when you're going to do a lot of deletes. And you're going to do a lot of deletes that aren't from the head or the tail, especially the tail. Tail deletes are not expensive at all for arrays or data structures based on arrays because it's not going to do a copy. All it's going to do is move the capacity integer down 1 or decrement the capacity number. And so that's not a big deal. But if you're removing them from the middle, it's actually going to copy all those elements back down, and that becomes a huge slowdown. So only use list when you're doing lots and lots of random deletes. And the third thing that was interesting to us is that reads are basically similar, but mutable map is the fastest, considerably faster than immutable map. And Java concurrent hash map sort of splits the difference between the two, which I found very interesting. Hopefully the Scala team will improve the performance of the containers in the future. I'm certain that they can. They're very bright people. And there's really good tools on the JVM for profiling and optimizing these things. And I think in future releases of Scala, they'll probably be able to correct some of these performance problems and some of the immutable data structures. Somebody came up to us and said, hey, there's 212, 211 is very old, maybe you're doing something wrong, so we did 212, and we found the same thing. Anyway, so hopefully maybe in 213 or 214 they'll optimize these things. So how does all of this knowledge help us design software? Well, the first thing to know is, are you writing a piece of code that's designed to be high throughput or low latency? After you identify that, you only want to optimize and profile inner loops. You want to look at your disk usage, your CPU usage, and your network usage to figure out which one of those is the highest. That will tell you which kinds of operations are likely causing the system to slow down or not running as fast as it could. And then finally, when you identify those slowest, most expensive operations, you want to reduce, cache, delay, or eliminate those expensive calls. So thank you to the Credit Karma folks that gave me so much support, and the Scala Days staff for being such wonderful hosts. Thank you. Questions? So the question was, do you have any ideas why immutable map is so much slower? No, I really don't. I haven't profiled immutable map really deeply to try to figure out what might be the source of these issues. If I had to guess, it's because they tried to make them the basic storage container being in that pair, that tuple object that they use. If I had to blame something, that's what I would blame. That's purely an intuitive guess backed by no hard facts. If somebody knows the answer to that question, I'm all ears.
When you said lists and seeks, did that include vector?
Anything that's array is what you want to go for, and anything that's based off of the linked list style lists you want to avoid. I'm not very good at remembering what maps to what. I tend to just use index seek everywhere. If you look at my GitHub, you'll see that I actually rehabbed a compiler plugin recently, and I did make heavy use of list, but I was following the pattern of the original Lightbin developer there, and I was going for least change. So I'm not being a hypocrite if somebody wants to go to my GitHub. List is really great when you're doing lots of deletes, and this code was doing a lot of recursion and a lot of deletes. Sometimes it makes sense. There are cases where list makes sense. That's absolutely true. But most of the time, when you're in that inner loop, you're going to want to use an array. Unless, like I said, you're doing lots and lots of random deletes. If you have stack or queue-like functionality, array is a really great backer for that. No, that's a good question. So the question was, since we're on the JVM with garbage collection, how do we deal with that impact on latency? The short answer for that is that malloc is very expensive. And the truth is that things that lead to performance bottlenecks, high latency, slow throughput, are roughly the same things that lead to garbage collection taking a long time. If you properly optimized your application, garbage collection should not take a long amount of time. The other thing is that garbage collection is sort of like that one-of operation that we talked about when we were talking about batching the database writes. And when we're talking about that, we were basically saying that there's one user out of 100 or one user out of 500 that's just going to take one for the team. Their request is just going to be slower than everyone else's. And that's probably a good trade-off most of the time. The GC is basically the same thing. Somebody's going to get unlucky. The way Google deals with that, just for reference, is they do everything twice. And so it's, instead of only one out of every 500 getting unlucky, you'd actually have to get one out of every, was that 250,000? 500 squared. So yeah, if you did every operation twice, then you would reduce that by a massive amount. But even at Google, there's that one user out of 4 users out of every million that just get unlucky, and their request is going to be a little slower because they hit a GC. But if you did your application right, that extra overhead is like 30 milliseconds, right? If you're getting multiple second garbage collections, you need to work on that. And you're probably allocating way too much memory. Yes, please. So The easiest answer to the first place to look is always run a profiler. The JVM has a really excellent profiler API. There's a lot of good tools that make use of it. Some of them are free and packaged with the JVM. So that's where I would start, right? Naively not knowing anything else about the application. The other thing I would say is that the kind of pipeline that you were describing, you would have 4 or 5 nodes in together, strung together. I was really talking about 4 or 5 applications strung together. But the same concepts and same things still apply. So in each of those individual nodes in a pipeline would still have its own inner loop, right? Its thing where it's doing its request. In a database kernel, what you would see there is you'd have several XOs. They're called XOs in database parlance. But they're the same thing that you're describing. And they would have buffers in between them. And they would each, when an XO is called, it simply runs until its buffer is empty. And then the next one gets scheduled. I think similarly, you would probably see the same sorts of behavior in what you're describing as in a database kernel, where one of the XOs would run much slower than the rest of them. And you would find that XO by the fact that its input buffer was always full. So it would be the same sort of thing in what you're describing. You would look for the guy who's called the least. And the next one downstream is likely the problem.
You made a claim earlier about non-blocking I/O and how only if CPU is a bottleneck would it impact latency / throughput.
Correct.
But I guess frameworks like Play use Akka and Netty precisely for the reason that they can free up those thread pools with non-blocking I/O, which in turn has an implication on latency / throughput.
It does.
So is this a contradiction to what you said? If so,
no.
Yes. If not, why not?
No, it's not a contradiction, actually. What I said is that if network I/O is what you're maxed out at, and you apply asynchronous, you're not going to improve your application, because what it's going to do is reduce the CPU, right? You haven't actually saved what's going on in the network. You already had 75% of your CPU always empty. So every time a request came in and needed some CPU time, it was always available. So that's why it doesn't have an impact on latency in that particular case. That being said, if you're doing the number of I/O requests that you're doing in some of these applications that you described, they may have a couple thousand concurrent writers. And that might easily overwhelm the CPU. The overhead that they induce might easily overwhelm the CPU. So in their use cases, they would want that. In addition, since most of the time they're acting as proxies, in a lot of cases they're acting as proxies and sitting on the same machine, they want to be as efficient as possible anyway. Plus the fact that there are third-party applications sort of talking about, like, I'm better than the implementation you can do yourself. You really should do this stuff correctly anyway. Because in their use case where they originally wrote this for, maybe that box was mostly CPU free, in which case they didn't need to do their asynchronous optimization. However, there's use cases that those of us probably even in this room have used where they needed that CPU free. And so that's why they would have done it in those libraries and those applications. It's much harder code to write. I personally prefer writing asynchronous I/O, especially on the network. It's actually easy to write in some cases, but the bugs are so much more subtle and so much more difficult to find. And really, you know, this gray hair is probably from one of those, and this one's probably from a different one. So there you go. Is that it? All right. Thank you, everybody.
I have a question.